So let's consider the following question. What are the subgroups of Z? And we're going to think of Z as an additive group. To answer this question, let's start with an example. So given A, which is an integer, let's define the set AZ, which is going to be equal to those integers, so for every n in Z, such that n is equal to k times a when we have k is any integer. This is a subset of the integers. For example, I can talk about 2z, which would be 0, 2, 4, 6, 8, etc., with also -2, -4, etc. And why is this a subgroup? Well, what do we have to check? We need to have the identity. We need to have inverses, which this set is going to have. And then we need closure, which is when we notice that if we take a multiple of 2 and multiply it by another multiple of 2, or not multiply it, but actually add, this is the additive subgroup. So if we add a multiple of 2 to another multiple of 2, we get yet another multiple of 2. So this is a subgroup. And now that we found an example, or a class of examples really, one for each integer, we have this theorem, which more or less says that this is the only thing that can happen. So the theorem, precisely stated, is as follows. Let S be a subgroup of Z, then S equals AZ for some A in Z. Now, to prove this theorem, it's going to take us a couple of steps. One thing I'll do for clarity's sake is every time I invoke one of the 3 properties of a subgroup, I'll mention that and I'll put a pink dot next to them so that it's obvious when we're using those axioms. So let's start by, so we have S is our subgroup. Now we want to say, so 0 is going to be in S. That is just the identity axiom. I'll put a dot there. If 0 is the only element, so now we're going to do 2 cases. Maybe a period would be better here. If 0, if S equals 0, i.e. it's the only element, well, this is also 0z, then we're done. If not, there's some n in S which is not equal to 0. So now, by the inverses axiom, both now n and minus n are in, maybe this is a better way of writing it. Minus n is also in S. That's the inverses axiom. And so we can see that either n or minus n is positive. So maybe I should write that. N or minus n is positive. So the conclusion is that S contains a positive integer. Now, we wanted to prove that S equals AZ for some A. So which exactly A should it be? And what I want to claim is that let A be the smallest positive integer in S. This exists because I just showed that S contains a positive integer, and because positive integers have an ordering, and there's the smallest positive integer, the ordering, I guess we could say it's well ordered or something like that. But really, it's just, we know it has to contain a smallest positive integer because it contains 1. We can just keep going down. There's a finite number of things to check. Once we have, once we know that there's a positive integer, there's a finite number of things until we have the smallest positive integer. So if A is the smallest positive integer, now I want to claim that AZ is in fact S. So now to prove this, we'll do it in 2 steps. First, we will show that AZ is contained in S, and then we'll show the opposite, that S is contained in AZ. Let me erase this just for a second. So if AZ is an S, that is the same thing as saying that KA is a member of S for every K in Z. So let's think about all possible K. So if K is a positive integer, well, we have then Ka is equal to A plus dot 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 plus A, and this should be K times, which by the, well, this is going to be the closure axiom, and then the closure axiom using induction, because closure axiom tells me that A plus A is in, and then do A plus A plus A, and A plus A plus A plus A, etc. until I get to K times, so I've just used induction. But then that tells me that Ka is in S. If K is a negative integer, then, well, all I need to use is the inverses axiom and then the positive, and then the version that I just proved here works. So that's good. And if K is 0, well, 0 is already in S by the fact that S is a subgroup by the identity axiom. So K0, well, I already know that. Okay, so now we have shown this half of the equation, or, well, of the theorem, really. It's not an equation. But now let's show the opposite half. S is in a Z. Now, to do this, it's so we're just going to say, so expanding definitions, what that's going to give us is, so if n is an S, then that means that n equals Ka for some K. Maybe I should erase this. That will give me a little bit more space here, maybe. That'll be nice. So pick n and S. So maybe, so n and S. So now what I want to do is I just want to write out what n is. I want to divide n by a with a remainder. So that'll be n equals some other number, which I'll call qa plus a remainder. So when I say division by remainder, this is just some elementary arithmetic. If I just have like a number line or something, right? I divide up my number line by lengths of a, and if I have my number n somewhere in here, what all it's saying is I can go, this is, I guess, 3 times a plus something that is less than a, r, where r is less than a. And this sort of picture, I think, kind of shows it. So the important thing here is that r is less than a. And of course, it's greater than or equal to 0. So now that I've written n in this way, I'm going to claim that r equals 0. If I'm right in my claim that r equals 0, then n is equal to qa, and I just need and then q is the k that I need for this claim right here. So if I finish this claim, then I will be done. So now I'm going to use the fact that we proved up here that AZ is contained in S. So in particular, QA is in S by the fact that AZ is in S. And so as QA is in S, we already said that N is in S. So R, which equals N minus QA by the closure axiom, is also in S. We said that R is in S, but R, wait a minute, R is a positive integer that's less than A, that's greater than or equal to 0. But R is less than A, which means that R equals 0, as desired. And that concludes the proof.